Hello everyone. In this video we're going to talk about flywheel calculations, or basically selecting an appropriate mass for a flywheel. Now, what is a flywheel? Flywheel is a reservoir for kinetic energy. It stores the kinetic energy of the system when the RPM of the rotating shaft, any that it is in the system, is basically reduced over some period and then increased over another part of the period or cycle of the system. And so when it is increasing, it is going to store that kinetic energy. Here, this is a rotary kinetic energy. So, and the flywheel is just a pure rotating device. So it is going to increase that energy into itself, right? And then when the system's RPM goes down, it can give it back to you. And so it can reduce the fluctuation watt in the energy of the system, and it can make the system run smoother. And you have seen flywheels in lots of different machines. You can see it from inside the engine. You can see it in machinery like crushing machinery. That's something that is used for punching and creating objects under press and so on, right? So here are some examples, right? Here in your engine in the car, you probably have seen this disc here, right? This heavy disc, and you might say, what is it? Why do I have this? Well, because your engine RPM does change. You know, each piston, when it moves inside the cylinder through this conrod, right? This mechanism that you see here, this one is a slider crank mechanism. And the RPM of the crankshaft, which is the result of this piston going up and down, this RPM, this omega, does oscillate. Okay, it's not constant. Even if this piston goes up and down at a constant velocity, the output omega is not constant. Now, in reality, it's not even going up and down constant speed, okay? Because when the explosion happens, it is going to go down much faster and with acceleration. So the omega of the crankshaft does change. And if this highly variable omega of the crankshaft directly goes to the transmission and then directly goes to the car tires, right, or the wheels of the car, then you are not going to be able to maintain the speed of the car at a constant value. So the goal of this flywheel is during a cycle, when this omega changes between some minimum and some maximum, which we're going to show by omega 2 and omega 1, where omega 1 is like omega max and omega 2 is omega min, then the goal of this is when it goes down, it basically releases some of that kinetic energy that it stored when it was going up. Okay, and that kinetic energy again is what? 1/2 I about the center of it times omega squared. Okay, so it acts like a reservoir of mechanical energy, just like what you have for basically a capacitor, right, in electric circuits, or what you have for an accumulator in a fluid system, that they store basically energy, electrical energy, fluid energy, or anything. So for solid objects also, the equivalent component is called the flywheel. By the way, the pictures and the equations that I have here are taken from the book Kinematics and Dynamics of Machines by G. Martin. This is one of the best books out there on mechanism design and analysis and machines. It's a very, very good book. So let's talk about how do we pick an appropriate flywheel for the system. So here, for simplicity of calculation, we assume that all of the mass of the flywheel is around a radius of r. So all the mass is right here. And this omega that it is spinning with is variable. It goes between omega 2 and omega 1, or the velocity of a point on the rim, v, goes between what? Between v2 and v1, where v equals r times omega, as you know from dynamics. And in reality, the flywheels are not internally hollow like that. Okay, if you look at this flywheel, you see it's not hollow here, although some of them, like this one, might be. This one that you see in used in a punching machine, you see that it has hollow parts. So not all flywheels are designed hollow. Some of them do, but if they do, they try to have about 90% of the mass around the radius r, and the other 10% is basically the mass on these arms and the center hub. Why do they do that? Because if you make the mass of the object further away from the center, then this entity I is going to go what? Is going to go up. And so in order to give this reservoir more capacity for storing energy, they need to bump up this moment of inertia, and they do that by making the middle parts hollow and moving the mass further away from the center. Okay? So here, for simplicity, that's what we do. So we use a simple formula for I. If we assume all the mass is at radius r, then we can approximate this by m times r squared. Okay? If it's a complicated object, it's not as simple as what you can see. So here we try to relate that I to the mass of the flywheel. Okay, so now let's talk about how we go about selection. So as I said, we show the maximum and minimum angular velocities by omega 1 and omega 2, and the average of the two by omega. So here omega equals what? Equals omega 1 plus omega 2 over 2, okay? And similarly, if you talk about velocity of a point on the rim, then velocity v is between v1 and v2, and we can say that the average velocity v is v1 plus v2 over 2. Okay, and if you want, you can always go ahead and add what? You can add an average here if you want. If this is a more appropriate notation for you, you can do it that way. Therefore, here you get both averages here and here. Good. So here we define, not that C, sorry. Yeah, this C does not have anything. It's this omega. My bad. We define a coefficient here called coefficient of fluctuation, C. Okay? And this C is defined as max minus min RPM, or max minus min velocity, divided by the average. So it's the range divided by the average. Okay? We call it coefficient of fluctuation. And it shows the percentage or how many times the range is bigger than the average, or what percentage of the average is the range, or the total fluctuation, the total change. In real world, in practical applications, we make sure this C is not more than 0.2. Okay, and we use 0.2 for crushing machinery, right? The ones that have a lot of change in angular velocity, like here. If it's for electric generators, we use a much smaller number, like 2 over 1,000, okay, 0.002. So it typically changes between these two numbers, this C. Now, in terms of C, since V1 minus V2 divided by V average is C, if you cross multiply, you get V1 minus V2 equals C average. Also, since V bar equals V1 plus V2 over 2, 2V bar, if you cross multiply, will get V1 plus V2. So you see here, you have two equations, 1 and 2, that if you know your V bar and if you know your C, you should be able to solve for V1 and V2. Or if I give you V1 and V2, then you should be able to solve for V bar and C. Okay, typically you know two of the unknowns, and you solve for the two others in these two equations, 1 and 2. Now, as I said, since we assume all the mass is concentrated around the rim radius, IC can be approximated by mr squared. So the kinetic energy will be 1/2 mr squared. So this mr squared, let's go up, make sure. Yes. This mr squared is your I that we replaced, and you have the 1/2 and you have omega squared, and then you can call this r omega squared as v squared. So kinetic energy, of course, can also be written as 1/2 mv squared, but this v is not what? This is not the v of the center, because that's 0. This is v of a point on the rim. And you can use v average if you want. If you want to go with the same notation as above. Okay, and this omega is also omega average. Now, as I said, you have scenarios where V is at the max, V is at the min. The total change in the kinetic energy, the maximum change in the kinetic energy that you should store in the flywheel can be written as, if you show it by E or delta K, is 1/2 m V1 squared minus 1/2 m V2 squared. Multiply both sides of equations 1 and 2, then you get this equation. Let me show you. So you have V1 minus V2, V1 plus V2. If you multiply, you get V1 squared minus V2 squared, and here on the right side you get 2CV squared. Okay, so you get this equation, and now this side of it is what you have over here. So I'm gonna plug in instead that 2CV squared up there. And so E is going to become what? Is going to become 1/2 m times 2CV squared, right? And these two 2's would cancel each other, and your E is going to be mcV squared. Okay, again, here you can use V bar if you want. And we use this formula 6 to calculate the required what? Mass for the flywheel. Okay, so this is equation 6, as well as equations 1 and 2 are typically used for the design of the flywheel. Now let's look at a physical example here. So here we have a punching mechanism where you have a motor, and this motor is driving this flywheel through basically timing belts. The RPM of the motor is 900. The RPM of the flywheel goes down to 150 through the reduction, but it gets higher torque. Then the flywheel is driving your crankshaft here, again through a gear, or through between these two is gear. So your RPM goes down further down to 30. And so the crankshaft rotates at 30 RPM, and it drives this slider crank mechanism. It makes this piston go up and down. And when this piston goes up and down, you have a metal sheet plate that you want to punch a hole into. You put that plate on this die, which has a hole already. And when this punch drives through the plate using a lot of force that is in this member, right, this vertical component of that, will force that punch through the plate, makes the hole in the plate, and it punches the plate basically. Okay, so that is your punching mechanism here. And of course, because of this slider crank mechanism, that is just like the car, here is the opposite of that. The crank is driven and through the motor, and the force is applied at the piston. But the overall idea is the same. You have oscillations in the RPM of this crank because of the force of the punch being applied on the system. And so you need a flywheel here to keep the mechanism, the system running smooth. So you're not going to directly connect the motor to the crankshaft. You're not going to put that motor right down here. Use a flywheel in between so the system can run smoothly. Okay, now, Let's talk about what kind of plate is this. This is mild carbon steel with a shear strength of 45,000 psi. The thickness of this sheet metal here is 1/2 inch, 1/2 of an inch, and the diameter of this hole that you are going to punch is 3/4 of an inch. So we show this diameter by D, we show the thickness of the metal by T, and the strength of the metal for shear, we show it by S. Now, we're gonna punch 30 holes in each minute, and we want to pick an appropriate flywheel. For the coefficient of fluctuation C, we go with 0.1. Remember, it's between 0.002 and 0.2. So here we pick a parameter for a value for 8.1. Good. Also here in this diagram, we have force of the punch versus displacement of the punch. And if you have sensors, force transducers, that you can plot it, the force versus displacement is some kind of peak function, some kind of bell curve, kind of, but it's not exactly bell curve like that. This is the actual force versus displacement or time. Now in this case it's displacement, but also I have some times on the graph as well. Okay, and remember we do 30 punches per minute, so every punch will take 2 seconds. So 2 seconds is the entire cycle time or the cycle time for one punch. Now out of that 2 seconds, only 1/3 of a second is used for punching, and the other 5/3 seconds is just when this mechanism goes back up and then comes down. Okay, so the only the time that the actual force is exchanged between the punch and the sheet metal is only 1/3 of a second, or 1/6 of the whole cycle. Good. So now let's keep moving. The first thing we need to calculate is the V of a point on the rim, which is R times omega. Now in this case, omega that you have for the rim is 150 RPM. You multiply that by pi by d over 60 to convert it into feet per second. Remember, this unit here is not, this is not omega. I don't have omega here. I have n, which is in RPM. And you know, RPM is related to radians per second. So I'm not going to use this formula. I'm going to use this formula, which is for diameter and for revolutions per minute. So 150, the diameter of the rim here is picked. It's suggested to us to go with radius of 1.5 or diameter of 3 feet. So remember, when you design a flywheel, there is M that you need to know, and there is R and C. So there are 3 parameters that you need to know. C you pick based on your application, you pick a value of C. R also, to make life easier, you also pick a value for R, and then you'll find M. Okay, so we are not going to do both of them. We're just going to pick what? We're just going to pick R and go for M. So here we choose a 3 feet diameter, 1.5 feet radius for the flywheel. And because in design you typically have more parameters than the equation, so some of the parameters you have to choose and move forward and make sure that the equations work. Otherwise you have to go back and fix it. There will be a cycle, right? A design cycle. So here the R we picked, and so we go here forward and we find the velocity of the point on the rim on average is 23.6 feet per second. Good. Now, since I have my V and since I have my C picked, both of these, calculated, V is picked, and C is picked, I go to equations 1 and 2. Now in equations 1 and 2, the right-hand sides are known. So I can come back here and solve for V1 and V2, although the problem did not really ask for it. But if you want to know what are the maximum and minimum velocities that my system can have, as I said, I have the right-hand sides of 1 and 2, so I go here. V1 minus V2 is C times V, which is going to be 2.36. V1 plus V2 is 2 times V, which is 47.2, and I can solve for V1 and V2 to be 24.8 and 22.4 feet per second. Okay? Now, let's go about calculating the mass. So here, as I said, the thickness of sheet metal is shown by D, diameter of the hole, T, by diameter of the hole by D, and the shear strength of the metal here by S. Then the required force for punching, if you neglect dynamic effects and you just calculate it based on the static assumptions, is the surface area of the hole, which is pi times D times T. Remember, pi times D is the circumference of the hole multiplied by thickness of the metal. This is the external surface area of that cylinder of the hole, right? And if you multiply that area by the strength, you should get what? You should get the force. And so we plug in the numbers, and we need the at least 53,000 pound forces so we can perform the shear in a static manner. In reality, you need more than that, because your punch is moving too, and it has masses, and it has to be accelerated as well, and it's not really a static operation, so you need more than this force really. But this is like the simple base calculation that you need to have. You always have a safety factor, but this is like the minimum amount of force that you need. And now we need to calculate the required energy stored. We need to calculate the left-hand side of the 6. How do we calculate that? This E is the change in kinetic energy, and it's also equal to what? Why kinetic energy changes in the first place. Why? As we talked, because this punch will hit the sheet metal, and so it slows down, and then later it picks up the speed through the flywheel. So the reason that you lose the RPM or V is because of the impact. So the energy of the impact, which is equal to the work done by the punch on the sheet metal, is equal to this change in kinetic energy, and also it's equal to the energy that your flywheel has to store. So how do I find this E? Instead of E, I calculate, as I said, the work done on the metal by the punch. And the work done by the metal on the punch is the area under this curve, right? So if I calculate this area under the curve of force versus displacement, this is the total work done on the sheet metal, and this is the energy that should be stored in the flywheel to provide the punching operation. So here I need to calculate this area under the curve, but unfortunately we don't have this graph here. We don't know here F as a function of displacement, right? Let's call it X. This function is what kind of function, so we can integrate it. We don't know. So here we do an approximation, and we approximate this shape by what? By a triangle. So we say this is something like this. We approximate it by a triangle, where this F is that F that we calculated, 5,300, right? And how much displacement would you have? Well, how much displacement do you need to make the punch in the hole? How much does the punch move into the plate? As much as what? As much as the thickness. So this distance from here to here physically is equal to what? Equal to T. So we multiply that force by this T, and we divide by 2 to get what? The area of the triangle. and we approximate the work that needs to be done. So W equals 1/2 F times T, and you get 1100 pound force feet total work that you need, and that is, as I said, equal to the energy that you need for punching. Now, question. Is this energy all coming from the flywheel? Well, you might say yes, based on what you said so far. True, but a small portion of it is provided by the motor as well. Why? Because during the whole operation of the punching, the motor is injecting the energy into the system. It's not like during the punching we turn off the motor and just let the flywheel drive the system, drive the punching system. When the system is punching, when this punch is going through the metal, not only flywheel is releasing its energy E, also this motor is injecting some energy into the system as well. And whatever this energy is, if I call it E prime or E of the motor plus E of the flywheel together is equal to all the energy that you need. So this W is equal to E of the motor plus E of the flywheel, where E of the flywheel is this formula that we had. But we need to know how much motor is injecting energy so we can reduce that. How much is it? So, remember, at the end of the day, flywheel is a passive element. It does not generate energy of its own. So all of the energy that you really need, all of that 1100, at the end of the day has to come from the motor. But motor does not generate such peak energy like that. Motor has a constant energy through the cycle like this. And so this area under the curve of the motor should be what? The same as all the energy you need for punching. So if you want to know how much is the force from the motor, you have to divide that 1100 by what? You have to look at the times that you have. That 1100 pound force is equal to the power of the flywheel times the time that the flywheel has to inject it. It's also equal to the power of the motor times the time that the motor has to inject that energy into the system. And as you can see, the time that the motor has is 2 seconds, but the time that the flywheel has is only 1/3 of a second. So clearly you see that the power of the motor is going to be a 1/6 of the power of the flywheel at any point, at this peak, right? So during the punching operation, the motor will inject this much of energy of it into the system, this much, just this small triangle, this guy here. How much is it? Remember, the whole big triangle is 1100. This one has the same height, but a 1/6 of the width. So the area under the curve of this is 1100 divided by 6, which is the ratio of 1/3 and 2. This much of it is coming from the motor. The rest of it, which is this green area here, is what your flywheel has to provide. Okay, all of this green area has to come from the flywheel in a short time. The rest of it, this red one, comes from what? From the motor. So really this guy is 1100 divided by 6. From here, if you solve for the energy required by the flywheel, it is 1100 minus 1100 over 6, which is 183. So 1100 minus 183 is 917 pound force feet. And now this is that energy that you need from the flywheel. It is 900 and what? 17, which is equal to mass of the flywheel times the coefficient of fluctuation times the average velocity squared. And if you plug in all the numbers, you see that we need at least 530 pound mass for the flywheel at a radius of 1.5 feet to be able to achieve this punching job. Okay? So hopefully this video was useful to you and you learned some basics about calculating the required mass for the flywheel, and I'll see you in the next video. Thank you.